for chapter 26, we talk about the resistance and current. So it will be a simple chapter, a very simple chapter, because it's nothing but V equals IR. I suppose you should have learned it in second analysis, but we try to see it in a V6 point of view. But actually, it's not so difficult, I think. So for current, it's something like any isolated contacting loop, regardless of whether it's an excessive charge, is all at the same potential. No electric field can exist within or along its surface. So any something, yeah. So it should have the same electric potential. So now, if we just insert a battery here, if we insert a battery here in the loop, the conducting loop is no longer at a single potential, because as you can imagine, this potential should be higher than this point. So the electric field, there should be some electric field going from this point to here, and you can imagine the electron will go from the other way around. But actually, when the physician know there are some current, something called current, they don't know there is something called electron yet. Electron is something like 100 or more later than they find, or there are some particle called the electron. And in chapter 28, I think you learn the Hall effect. Then that is one of the experiment to tell people that there should be some negative charge particle rather than positive charge particle. At that time, they may consider there are some positive charge particle going in this direction with the same direction of the current. So they define the current in this direction. So yeah, they may consider going from positive to negative is trivial. They don't get many conflict with other theories. So it's fine for circuit theory. You can consider the currents going from the positive to the negative. But actually, there should be some electron going from the negative end to the positive end. So exerting force on the internal charge causes them to move, thus establishing a current. So we will define the current as the dq dt. You take the derivative of the charge with respect to the time. So it is the current. So if it is just a constant current, then it's nothing but Q over T. But if the current is not necessarily DC current, it may be an AC current or any shape, not necessarily a single sinusoidal. It can be a multiple sinusoidal, as you will learn in signal and system in this semester. Then you will learn that any function, any time domain signal can be transformed into the frequency domain. The frequency domain of the signal is nothing but xt exponential to j minus t dt from minus infinity. So you will calculate it in signal and system in this semester later on. So there's the law called the Kirchhoff current law. I suppose you have learned it in circuit analysis. But actually, it tells you that a conductor with current I0 splitting at the junction in two branches. So we have I0 going in this junction and I1, I2 going out. So I0 should be I1 plus I2. So it's nothing special. even though this line is something like this. This one does not touch this one, so in this case, I0 is still equal to I1 plus I2. But usually in circuit analysis, I usually consider all the current going into a node to be zero. Then it'll be all fine, because sometimes when you need to consider some current going in and some current going out, then you get uh, confused by yourself. Uh, so I usually consider some current going into a node, then it will be less probability to commit mistakes for the calculation. So this is the Kirchhoff current law. It just tells you that the charge is conserved. So you can just add up all the current going into a node, which is equal to the current going out from the same node. And here we define another variable called the charge density. But this is different. Usually when we define a variable, we usually try to write this variable equals to something else with an expression. But here we cannot really define j by a function of I, because we will define the current density by this surface integral. This surface integral will be equal to I. So it's different from the Gauss law. The Gauss law, which has a circle here, which means that it is a closed surface. But here it doesn't necessarily to be a closed surface. It can be a surface, maybe like here, So you consider order J. J is like a vector field. So at different position, you can consider the J are different. So through this graph, you can consider the charge. We try to go from a wider wire to a narrow one. Then the resistance will change at this part. So you can consider there are some water flowing down. So then the charge density is somehow like how the water flow. And we consider the surface integral of the J over a surface, and then it will become the current going through this area. And if it is positive, which means of course we may need to define the A vector. For example, if we define dA pointing to the right side, if it is positive, which means that the current going to the right side, and if I is negative, then which means that the I is going to the left side. But remember that I is not a vector. I is a scalar. Although we will tell that the I is going to the left, going to the right, but actually it's not a vector. The current density is a vector. So the dA is vertical perpendicular to the surface element of the area dA, which is the same as the mathematics in the Gauss law. But for that one, we consider closed surface, but here we don't necessarily consider closed surface. So an integration is taken over any surface cutting across the conductor. Then we can consider the current going. So we just cutting through the conductor. Then is the current going through this part. So the current density has the same direction as the velocity of the moving charge if they are positive charge. positive charge. So that's just like what I have mentioned. They usually consider positive charge. If you consider it's a negative charge, then you should consider the negative direction, the opposite direction. So here there are some hardcore physics stuff, but it is, in my opinion, not so really important. But the physics guy will consider this very important. Yeah. So here we have a wire. We have a wire. We consider the length is L. To consider the length is L, and the velocity of the charge is Vd. We call the drift velocity, and there should be some E field pushing the charged particle, because you should have some battery, and the battery will create an E field to push the charged particle to move. And also we will have the as the charged particle move, there will be some current or the current density. So we have something like this. They should point to the same direction. They should point to the same direction. So you can consider a battery. A battery is somehow like this. So that the current will going from the right to the left. So here we consider Q is NALE. A is the cross-section area. This is the cross-section area. This is the length. So this is the length. So AL is the volume of this part. And N is the charge density. Is the charge density. Or the number of charge in a unit area, in a unit volume. So charge in the volume AL, and N is the number of charge, and E is the elementary charge amount. So when we multiply all of them together, is the total charge in this part. So they consider the charge is moving in a constant speed. We call it Vd. And the length is L. So the time the charge takes from going from this end to this end will be T over L. T equals L over Vd. So it is very easy. You should learn it in primary school, I think. I is Q over T, because we consider the current is uniform, so we don't really need to take the derivative. We can just use I equals Q over T, and we just substitute T to be here and then Q to be this one. So L and L can be cancelled, and we have NE times A over Vd. We move it to the top. So we have NEAVD. And as long as we consider the J is uniform, so that we can simply write I equals JA. Originally it's an integration, but if it is uniform, then it's nothing but a multiplication, J times A. So J is I over A. So we divide A on both sides, then we'll have J equals NEVD. So the physician guy will consider this is a very important formula, but I don't use it for more than 15 years, I think, when I learned this stuff in 2004. Actually, I have not used this formula even once. I only teach it here. I only teach it here. But the physician will consider this is a very important formula. Yeah. So so the current is said to be the positive charge, and they are propelled by the electric field. Positive charge carry drift velocity. So Vd is what we call the drift velocity. Drift at speed Vd in the direction of the applied electric field, which is applied to the left. By convention, the direction of the current density is the same of the current arrow are the same direction as the drift velocity. Drift speed, drift velocity is related to the something like this. So it write it as a vector form. So J vector equals NE times VD. So it's something like a physics model. So you have a number of electron at the unit volume, and then E is the elementary charge. So you just divide the J, and then you get the uh, drift velocity. Actually, this drift velocity is not a practical value for a for a uh, for a electron or for a charged particle. It is just a imaginary velocity, I think. The charge doesn't necessarily move at the speed of Vd, doesn't necessarily move at the Vd. So here the product Ne, whose SI unit is the coulomb per cube meter, C per meter cube, is the carrier charge density. So let me finish this sample example. The current density in the cylindrical wire of radius 2 millimeter is the uniform across the cross section of the wire and is J equals 2 times 10 to 5 A per meter. What is the current through the outer portion of the wire between the radial distance R2 and R? So this is pretty easy. Yeah. So it's asked you to calculate the current for the outer part. So the area for the outer part should be the total circle, which is pi r square, minus the inner circle, which is pi r over 2 square. So you only consider the outer ring. So it is nothing but pi r square times 3 over 4. So which is 3 over 4 times pi times r is 2 times 10 to minus 3 quantity square. So this is 9.42 micrometer square. Okay, micrometer square. So and next I would be JA prime, and J is nothing but 2 times 10 to the 5th power, and then A prime is 9.42 mu m squared. So it will be 1.98. So it's very easy. It's something like a high school difficulty. I think. So for this one, it's a little bit more difficult. A little bit more difficult. So here we consider the current density J to be a function of the R. So of course, the RSS is something like this. So J is proportional to R squared, which means that the current density is 0 in the center and maximum at the outside, at the edge. So here we need to consider G dot dA, the integration. And actually, A is maybe you can consider pointing inside the page or outside the page. It is fine because we don't really consider it here. So, but actually, you can consider it's a cylindrical wire. So, so the charge density, the current density should have the same direction as the dA. So, which means that we can write it as JDA. So J is nothing but AR squared, and dA would be using the polar coordinate, which will become dA will become R dr d theta, R dr d theta. Yeah. Because you can consider like this. So this one is dr, and this one will be R d theta. This one will be R theta. Although this is not a rectangle, but if it is small enough, you can consider it's a rectangle. So it will become R times R d theta. So dA will be R dr d theta. So we times dr d theta. And actually we integrate from 0 to R, and theta is from 0 to 2 pi. Maybe this one should be R, capital R. Yeah, we still consider the outer portion, so that we consider the lower bound should be R over 2 here. Should be R over 2 here. We still we still consider the same outer portion of the wire, which means that we consider from R over 2 to R. So we integrate it from R over 2 to R. And this one is easy to calculate, which means that R over 2R, we have R squared R, so we have R cubed dr, and then d theta, no theta, so we have like this. So this is nothing but 2 pi, this is nothing but R to the 4th power, R to the 4th power over 4. So this one will become R to the 4th power over 4 minus R over 2 quantity to the 4th power over 4. A. Something like this. So we, after you plug in all the values, you can get the result to be 7.18.